Circles chapter 10. A circle is a collection of all the points in a plane which are at a constant distance from a fixed point. The constant distance is known as radius, the fixed point is known as center. Now this thing we have already studied in our lower classes. So let us consider a circle and a line PQ. Then there can be three possibilities given in the figure below. First one, we can see that the line and the circle do not intersect at all. So this is the first case 1. What is case 2? In case 2, the line is intersecting the circle at two distinct points. You can see that A and B. And we have the third case also, when the line only touches the circle at one point and does not intersects it. So it only touches the circle. So that is will be our third case. So when a line is intersecting the circle at two distinct points, in that case it is known as secant, S-E-C-A-N-T. So the word for that is S-E-C-A-N-T. And when the line is only touching the circle, it is known as tangent. So this is the tangent. And the point at which the line is touching the circle is known as point of contact. So this A will be point of contact. Point of contact. So now here we can see another case. In a circle we know there are infinite points, and if we try to draw different lines from that point, we'll see that from that point, say P, let P be any point on the circle, then from that point P we can draw one and only one tangent. If we try to draw other lines from that point P on the plane, we will see that they all will become a secant. So from one point on a circle, only one tangent is possible. Now here we can have the other one. Suppose we are having a tangent at one point of a circle, then only one more tangent can be drawn which will be parallel to that, and that will be at the end of the diameter, which is found by joining the 2 points. Here you can see that P dash Q dash and P double dash Q double dash, they are two tangents which are parallel to each other. So the tangents can be drawn only at the endpoints of the diameter, which will be parallel to each other. Now we have here one theorem also, theorem 10.1, which says that the tangent at any point of a circle is perpendicular to the radius through the point of contact. What does this mean? So here we are having a circle, and this is the tangent, and this is the point of contact which we have already discussed. So point P is the point of contact. In that case, this angle OPQ will be always 90 degree. That is, the radius and the tangent at the point of contact will be always perpendicular to each other. So how can we prove this one? Let us take any point on the line other than the point P. Now here, since we can see from the figure also, whenever we take a point on the line other than point P, it will be outside the circle. So that means in that case you can see that the length of OQ will be always bigger than OP. It can never be equal, because P and Q are distinct and Q is lying outside the circle. So obviously when a point, we know that a point which lies outside the circle, its distance from the center is always bigger than that of the radius. So in this case OQ will be bigger than OP, and so from this we can conclude that OP will be the smallest line segment. From point O, the smallest line segment will be OP, and from our study in our lower classes we have learned that the line segment is having the smallest distance from a fixed point which is outside a line is always perpendicular to the line. So that means OP will be perpendicular. OP will be perpendicular. Why? Because whatever point we can take outside the circle, and if it is lying on the line XY, then definitely it will be always bigger than the radius. So from this we conclude that OP is the smallest line segment and therefore OP will be perpendicular to the tangent. So this is our theorem 10.1. Let us revisit what is 10.1. The tangent at any point of a circle is perpendicular to the radius through the point of contact. Now we will go in exercise 10.1. So exercise 10.1 is a very simple one. Whatever we have learned, that only will apply. First one, how many tangents can a circle have? So in a on a circle, you know that how many points are possible. There are infinite points on a circle. So that means how many tangents we can draw on a circle? On a circle we can draw infinite tangents. How many tangents we can draw on a circle? Infinite tangents can be drawn on a circle. So let us write down the answer of question number 1. So answer question number 1. So how many tangents can a circle have? That is already we have discussed. So let us write that on a circle we have infinite points. We have infinite points. Therefore, on a circle we can have infinite tangents. We can have infinite tangents. Infinite tangents. And also it is very clear. It is also very necessary to make it clear that on a particular point we can draw only one tangent. So that is why we will write on a circle we can have infinite tangents, but at a point on the circle we can draw only one tangent. At a point on the circle we can draw only one tangent. We can draw one and only one tangent. One and only one tangent. So this is the answer of first one. Now let us go in the second one. Second one is fill in the blanks. A tangent to a circle intersects it in, that we have already discussed, that is in one point. Then second one, a line intersecting a circle in 2 points is called a secant. Then we have third one, a circle can have how many parallel tangents? At the most 2 parallel tangents. 2 parallel tangents at the most. Then fourth one, the common point of a tangent to a circle and a circle is called point of contact. So that is known as question number 2, fourth part is known as point of contact. Point of contact. Now let us go in question number third one, exercise 10.1, question number 3. So we will be solving that. What it says that a tangent PQ at a point P of a circle on the radius 5 cm meets a line through the center O at a point Q, so that OQ equal to 12 cm. Length PQ we have to find. Let us draw a figure for this. So suppose this is our circle and let this be the tangent and this is the center O. Now a tangent PQ at a point P of a circle. So point P is lying on the circle and also on the tangent. So this is point of P will be point of contact. Let us join O and P, and there is another point on the tangent and that is Q, and the distance of OQ is 12 centimeter, and OP, the radius is 5 centimeter, and what we have to find is we have to find the length of PQ. Now how can we find the length of PQ? By applying theorem 10.1. What is theorem 10.1? The radius and the tangent both are perpendicular at the point of contact. So here OP will be, since here OP is perpendicular to PQ and P is a point of contact, therefore angle P will be 90 degrees, and we can apply Pythagoras theorem, and applying Pythagoras theorem we will be getting the value of PQ. So let us start doing this one. Here P is point of contact. P is point of contact and OP is radius, and OP equal to radius. Therefore we can say that angle OPQ will be equal to 90 degree. Why? Because the tangent is always perpendicular to the radius at the point of contact. So next we will be applying Pythagoras theorem in right triangle OPQ. So in right triangle OPQ, we will be getting OQ square equal to OP square plus PQ square. How we got this? By applying Pythagoras theorem. So here we will write Pythagoras theorem. So this is our Pythagoras theorem. Application. Now what is the value of OQ? OQ is 12. So we will write here 12 square equal to OP is 5. So that is 5 square plus PQ is not known to us. So we will write PQ as it is PQ square. So 12 square is 144 equal to 5 square is 25 plus PQ square. And this will give us PQ square is equal to 144 minus 25, and that will give us PQ square equal to 119, and taking square root both sides we will be getting, therefore PQ equal to square root of 119 centimeter. So what is the correct option in our case? That is D. Therefore correct option is D. Therefore correct option is D. Now let us go in question number 4th one. So we will be doing question number 4 of exercise 10.1. So solving question number 4. Now what is question number 4? Draw a circle and two lines parallel to a given line such that one is tangent and the other is secant to the circle. So this figure will be drawing with a compass and a ruler. Here I will be drawing it roughly, but you have to draw it with compass and ruler, otherwise it has no meaning. So first what we will do, you can draw a circle of any radius. Suppose this is circle O, and draw a line and make the line such that it is not touching or intersecting the circle. So this is the line L, and now we have to take we have to draw two other lines. One will be touching the circle and one intersects the circle. That is, one is tangent, the other is a secant. So and this both should be parallel to the line L. So here this is the line M, and line M will be tangent. Then we will draw another line which will be secant. That means it will intersect the circle at distinct point, at two distinct points. So this is the line N, and line N is secant. So here L is parallel to M and L is parallel to N. M is tangent. Why? Because it touches the circle at only one point, and N is a secant. N is a secant. So with this our exercise 10.1 is complete. Now what we will be learning is more about we learn more about tangents, the natures. So number of tangents from a point to a circle. Now here we have a circle and a point. So there can be three cases in this also. This point P can lie inside the circle. So when point P is lying inside the circle, no tangents can be drawn. Here point P is inside the circle. So in this case, no tangents can be drawn. No tangents can be drawn. Can be drawn. Then we have second case, when the point P is lying on the circle. So in this case, only one tangent can be drawn. Only one tangent can be drawn. Only one tangent can be drawn to the circle. Can be drawn. And when the point P is lying outside the circle, then how many tangents we can draw? You can see from the figure, so we can draw two tangents. Two tangents can be drawn when a point lies outside the circle from that point. So two tangents can be drawn. Two tangents can be drawn from point P. Can be drawn from point P. So let us recall it again. When the point P is lying inside the circle, we see that no tangents can be drawn. When the point P is lying on the circle, one and only one tangent can be drawn. And when the point P is lying outside the circle, how many tangents can be drawn? Two tangents can be drawn. And this PT1 and PT2, they are known as length of the tangent. What they are known as? Length of the tangent. So here we have theorem 10.2. What it says that the lengths of the tangents drawn from the external point to a circle are equal. So theorem 10.2, the lengths of the tangents drawn from external point to a circle are equal. So how we can prove it? So here we are having this figure. So first of all, what we will be doing? Join O and P, and also join O and Q and O and R. Here Q and R both are point of contact. So for PQ, for tangent PQ, Q is the point of contact, and for tangent PR, R is the point of contact, and OQ and OR both are radius. So let us go in, we'll be seeing the proof of this. So proof is very simple, it's not difficult at all. So we'll derive it. Derivation is also not difficult at all. If you remember, here let's do this theorem 10.2. So as we have already discussed that whenever we have a radius and a tangent, then they are perpendicular at the point of contact. So here Q is a point of contact. Q is a point of contact. So we can say that therefore OQ will be perpendicular to PQ. Similarly, we also have OR is perpendicular to PR. Why? Because R is point of contact. R is point of contact for the tangent PR. For the tangent PR. Now we will be going in the because angle Q and angle R both have become 90 degree, so they will be right triangle. So let us go in this right triangle. In right triangle OQP and right triangle ORP, OQ equal to OR, OQ equal to OR. Why? Because they are both the radii of the same circle, radii of same circle, so they will be equal. Next one, OP equal to OP, OP equal to OP, that is the common side, common in both. And the third one, we can see that angle Q and angle R, that is angle OQP equal to angle ORP, both are 90 degree. Why? By theorem 10.1. Here also we have discussed in the beginning, that is OQ is perpendicular to PQ and OR is perpendicular to PR. So therefore we can say that by RHS, therefore by RHS congruence rule, RHS congruence rule, what we can say that triangle OQP is congruent to triangle ORP, and therefore by CPCT, what we can say that by CPCT, that is corresponding part of congruent triangles, we have PQ equal to PR. So but they are tangents drawn from an external point. We can say that tangents drawn from an external point are always equal. So this is our theorem 10.2.